The construction industry makes up over 9% of global GDP, but while productivity in other major sectors has skyrocketed, construction has completely flatlined. Before a crew can pour a single concrete foundation, the exact physical shape of the earth must be measured. If the underlying topographic map is wrong, the entire building project is compromised. Traditionally, establishing this ground truth meant deploying human surveyors to walk the site with tripod-mounted GPS and lasers. The measurements are highly accurate, but the physical process is incredibly slow. This leaves the industry trapped between two bad options: push through the mapping phase quickly and risk structural disasters, or map the terrain perfectly and bleed time and money before building even starts. Aerial drones initially looked like the perfect solution. An eye in the sky can sweep massive, complex expanses of land in a fraction of the time it takes a human to walk it. Take a rapidly growing area like Cluj-Napoca in Romania, where new concrete suburbs are pushing directly into dense, natural forests. From the air, a drone's standard camera sees a thick canopy of leaves. It cannot reliably penetrate that vegetation to detect the dirt, rocks, and sudden dips in the terrain hiding underneath. Speed is meaningless if the map requires engineers to guess what the actual ground is doing. A map with a blind spot is a massive liability for structural engineering. To survey from the air, operators typically use a technique called UAV photogrammetry. By taking hundreds of overlapping photos, software stitches them together to create a 3D model of the topmost surface, known as a digital surface model. Photogrammetry excels at capturing brilliantly crisp, textured details of man-made structures, like the sharp pitch of a roof or the smooth surface of a paved road. Looking at this cross-section, blue camera points stop at the canopy, leaving the ground blank. So teams deploy LiDAR, firing laser pulses that slip through leaves. Software then deletes the trees to map the dirt below, creating a digital terrain model. But LiDAR point clouds are relatively sparse compared to high-resolution photos. They struggle to capture the sharp edges, intricate textures, and clean geometry of buildings and infrastructure. Engineers were forced into a frustrating compromise: use a camera and lose the ground, or use a laser and blur the architecture. The solution to this problem is a spatial analysis technique called the Digital Feature Model, or DFM. In these profile diagrams, the logic is clear. Rather than forcing one flawed sensor to map everything, researchers divide the environment. They extract LiDAR data exclusively for wooded areas and isolate photogrammetry strictly for concrete and buildings. These targeted zones are then seamlessly stitched together to form a flawless, hybrid mosaic map. True precision is achieved by recognizing that these two sensors possess perfectly complementary flaws and using software to cover their respective blind spots. To validate this theory in the dirt, the hybrid approach was tested using drones and ground sensors on a complex land parcel in Cluj-Napoca. On this aerial map, you can see where the team manually measured 233 individual physical control points to establish an absolute baseline of the true terrain. Graphing the error margins, standalone photogrammetry drifted off reality by 21 centimeters. Independent LiDAR performed better, missing the mark by 13 centimeters. But the hybrid digital feature model reduced that vertical error down to a razor-thin 7.5 centimeters. Splicing the two datasets together essentially neutralized the individual errors of each system, proving the mathematical fusion is vastly superior to its individual parts. Surveyors now have a method to generate hyper-accurate topographic plans at the speed of drone flight, without sacrificing the strict safety tolerances that civil engineers require. This is crucial as global populations swell and the edges of our cities bleed further into dense, unpredictable natural ecosystems. Giving architects and engineers a perfect digital replica of reality before ground is ever broken removes the costly guesswork that has caused construction productivity to stall. To build efficiently, we need a complete picture of the terrain. Fusing these sensors brings both the wilderness and the architecture into a single, reliable digital focus.